This is my Calculus 1 course. Today we're going to do some more Precalculus review. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. Remember, the homework is not optional. It must be done completely and correctly, and it should be in order in your binder. And make sure that it's neat. So you cannot escape the homework of any math course. If you don't do the homework in your math courses, then you'll learn absolutely nothing. That's the way it works with math. So be sure to get that homework assignment done before going on to this class. So again, today we're just going to do some more Precalculus review, and then we'll move on to the actual calculus. So these are the topics we're going to cover today. Let's get right into it. So oftentimes when students take their first calculus course, you'll find that they don't really know how to simplify complex fractions. It's not something that's hard to do, but when students look at this, they kind of just freeze and they don't know what to do. So I'm just letting you know that this is one thing that you're going to be expected to do in your calculus course, your first calculus course. Your calculus teacher is not going to show you how to do this. He or she is just going to expect you to know. So I'm just letting you know that this is one of the many things that you need to know how to do. Now there's a fast way to do this. The fast way is just to multiply both sides of the fraction by the lowest common denominator of the fractions, and that will simplify the fraction immediately. But students don't really like that. They get kind of confused by that. So, and by the way, that's the fundamental principle of fractions, multiplying both sides by 4. The method that students typically prefer, not because it's faster, but just because it's easier to understand, is to interpret the fraction line as a division operation. So all we're doing is just dividing fractions, and when you divide fractions, remember, you flip the divisor and change to multiplication. So now we're just multiplying fractions, and when you multiply fractions, the way we do that is we multiply the numerators. 4 times 1 is 4, and we multiply the denominators. 2 times 1 is 2. So we can see that the simplified answer is 2. Now, you're not going to be expected to write this in your calculus course. You're going to be expected to go from here to there, and you can do it however you want to do it. But most students should be able to do this in at least, well, they should be able to do it in one step or no step. So you're expected to go from here to here very quickly. So again, that's just something you need to know. Let's do another problem. So again, and I think I'll demonstrate the other method, the faster method now, because this is the method that I use, and probably most mathematicians use, just because it's the fastest method. If you use this method for a certain amount of time, you'll eventually realize that this method is actually faster. So we're going to multiply both sides of the fraction by the lowest common denominator of the fractions. Well, this is not a fraction, so that denominator doesn't really count. You can think of it as 5 over 1, but still the lowest common multiple of 3 and 1 is 3. So multiply both those, and the reason this works so well is because the 3's they just cancel out, and so you're left with 2 in the numerator and 15 in the denominator. So literally in one step you can write the answer. But now that I think about it, it's probably best just to do it the other way, because the students might get confused if I do it that way. Typically students just want to see one method. They don't want to get confused with a bunch of different methods. So we're just going to do it the same way we did before, and we get 2 over 15. Same answer. Okay, so I want you to try number 3. And You know, a lot of students will say, well, I don't need to do this because I know how to do this. But even if you know how to do it, I want you to get some practice, because the purpose of this is partly to get you warmed up with math so you're ready for the calculus. So do number 3. Even if you don't want to do number 3, go ahead and do that problem, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 4, and when you come back, we'll do it together. Okay, we're back. 7. So if you got 27, excellent. Good job. So you're going to see complex fractions, and you're going to be expected to know how to do those. So just be aware of that. Your calculus teacher is not going to show you how to simplify complex fractions. In fact, you're going to be expected to do even more complicated complex fractions than you see here. This is just the basic stuff. So if you're struggling with this and you're not really sure, and you've never seen that before, then you're really not going to be ready for this course. So again, the part of the purpose of this class is to be a warning to you that you were supposed to learn certain information. If you didn't learn that, then you'll have to take my my previous courses. So next thing we're going to learn, or that we're going to review, is logarithms. So these are all the logarithm properties that we learned in my curriculum. These are all the properties you're supposed to learn in any curriculum, any K-12 curriculum in the United States. So these properties here we're not really going to use today because we just don't need them today. But these properties are going to be useful. The most important property is property number 1, which simply defines logarithms, tells you what they are. These properties can be used if you want to move more quickly. But these properties are just a result of property number 1. So you don't really need to know property 2 and 3. They're just something that help you go faster. Take a picture of those logarithm properties. Make sure you have a picture of those. And it says here, determine if the following values can be discovered without a calculator. Can we find the values of these without a calculator, or do we need a calculator? So then find the values. If a calculator is necessary, round your answer to the nearest thousandth. Okay, so we need to find the value of this expression. We might need a calculator, we might not. We're going to see. So you want to get your calculator ready. I'm going to be demonstrating how to use a TI-84 Plus. That's the calculator that we recommended in class number 1. Remember that. You don't have to use that calculator, but you should have a graphing calculator. They're much more easy to use, and you may need to use the graphing capability in upper math, so you really need to have that graphing calculator. But we don't know if we're going to need the calculator for this, so let's try to figure this out. We need to find the value of this expression, but we can't because we don't even know what this expression is asking. We don't know what to do. But let's set it equal to x. Let's just say that that expression is equal to x. This is what we call a logarithmic equation. It's a logarithmic equation. And logarithm property 1 tells us that we can translate that to a different form. We can translate it to an exponential equation. So if this is true, then by definition, this is true. That's what logarithm property 1 tells us. It's just a definition. It's not anything to be too nervous about. You just memorize it. So if you want to solve this equation, the solution is this. But you can go backwards, so that if you are given this expression, you can go to the exponential form. Anyway, long story short, we can see what the answer is. We're looking for x. X is 3. We did not need a calculator for that one. So the most important thing to remember is how to translate back and forth between a logarithmic equation and an exponential equation. If you can do that, then you understand the basics of logarithms. If you can't do that, then you understand nothing about logarithms. Is that clear? If you know how to translate back and forth between the logarithmic form of the equation and the exponential form of the equation, then you understand the basics of logarithms. If you do not understand that, then you understand nothing about logarithms. So that is the most important thing to understand, that property number 1 is something that you have to have memorized. And it's nothing intuitively difficult. It's just a definition. If you want to solve this equation, then x is defined to be this expression. That's all we're talking about here. When we say defined, we say that mathematicians just decided to make those symbols represent that concept. So we did not need a calculator. And so x, the number we're looking for, log base 3 of 27, is equal to 3. That's the answer. So let's try another one. We need to find the value of this expression, but we don't know what it means. We don't know what it's asking. We're stuck. So what we're going to do is set it equal to x. And then we're going to translate, or we're going to transform this equation into the exponential form. Now, I should have made it clear that number is the base. That little number there is always the base. This number always goes here, and this number is the exponent. Remember, a logarithm is an exponent, so if x is equal to the logarithm, then that goes in the exponent. So what did that do? How did that help us? The only thing that really did for us is it told us that we can't do this. We need a calculator. So in this equation, we could easily solve that. We knew that x had to be 3. I mean, that's obvious. 3 to the third power is 27. So x must be 3. The value of the logarithm is 3. But try to figure this out. We don't know what x is. There's no way for us to tell. We can estimate what x would be. It has to be somewhere between 1 and 2, right? But that's all we really know about it. So we have to use a calculator. So we're going to find x, but we can just find x by using this this notation here. So if you're using a different calculator, there's all kinds of ways to do this. But if we try to explain every single if we try to explain how to do this with every single type of calculator possible, then it would take 30 explanations just to do one problem. So we can't do that. All I can do is show you how to use the TI-84 Plus. That's all we have time to do. So you're going to push the green alpha button at the upper left. Push the green alpha button at the upper left. Then you're going to push the window button, the F2 window button at the upper left. Then you're going to use the arrow key, the down arrow key, to go to number 5 where it says log base. Press enter at the bottom right. And you should have something like this where it has a box there and a box there, and you just enter in the numbers. Then you press enter and we get approximately 1.3023. So that is the approximate answer. Actually, we're supposed to round to the thousandths place, so it should be that. So tenths, hundredths, thousandth. Okay. So how do we know thousandths place? Because it says right up here, round to the nearest thousandth. So in that problem, we actually needed a calculator. All right. So let's see what we can do for the next one. We need to find the value of this expression. We can't do it because we don't know what it's even asking. We don't know what's going on here. So let's set that expression equal to x. And let's translate to an exponential equation. And now we can see what x is. It's just the solution to this equation. If it helps, you can change 16 to 2 to the 4th power. You don't really have to do that. But we see that x is equal to 4. Did we need a calculator? No. So we did not need a calculator for that. So x is what we're looking for. That's log base 2 of 16. We just found that that's equal to 4. So there you go. All right. So let's try another one. We need to find the value of this expression. So we're going to set it equal to x. But do you notice something about this expression? We're missing a number right there. There is no number. If there is no number, it's assumed to be 10. You may recall that from my curriculum. You may have forgotten it, but now you remember. That's base 10. Base 10 logarithms are assumed to be special types of logarithms because base 10 is a very important base. The other important base is this one over here, which we'll talk about later. That's base e, e being some constant. So now we have the logarithmic form of an equation. We're going to translate to the exponential form, and we get the following. So again, it's so crucial to understand that number goes there, and this number goes there, and that number goes there. That's always the way it works every single time. You either remember it or you don't remember it. That's up to you. You need to make a conscious effort to memorize this, because if you don't have it memorized, then you really don't know anything about logarithms. If you want to, you can change that to 10 to the 3rd power, but you don't really need to. So obviously the answer is 3. Did we need a calculator? No. We did not need a calculator. So that was just a special problem because we had a special base. So what is the answer? X is what we're looking for. Log base 10 of 1,000 is equal to 3. Okay, so let's do some more problems. Now we have the natural log. So the natural log, we don't know what that means. We don't know what it's asking. But ln is just log base e. That's all it is. All right. And so now we just translate to an exponential equation. And you're probably wondering, well, what is that blue number? What is that? Is that a variable? It's not a variable, it's a constant. It's a constant number, and we call it e. We call it e because it's irrational. We don't want to write the whole non-terminating, non-repeating decimal. It's an irrational number. So if you want to, you can write 1 as e to the 0 power, and that tells us obviously that x is equal to 0. You don't have to do that step if you don't want to, but did we need a calculator? No, we did not need a calculator. Okay, so x is equal to natural log of 1, which is equal to 0. So there you go. Okay, so let's do another one. So ln is log base e. That's just the definition. So all this stuff here went there, and the natural log, or the ln, became log base e. I just want to make that clear. Okay, so we're going to set that equal to x, and then we're going to transform that to an exponential equation, and you can see now what the answer is. It's pretty obvious. X has to be 4. Did we need a calculator? No. No calculator necessary. So x is what we're looking for. That's log, or natural log e to the 4th. That's just equal to 4. So we just used logarithm property 2, or we just demonstrated logarithm property 2. But you don't need to use that you can just use the property 1 and that'll get you to the answer. These are just kind of shortcuts to the answer, but it's better to review the first property rather than to worry about the shortcuts right now. Okay, so now let's change ln to log base e, and now we're going to transform that to an exponential equation, and the question is, do we need a calculator? And the answer is yes. We can't do that without a calculator. It's not going to be easy. So we need to go to our calculator and find natural log 7. Now, your calculator has an ln button. You see this? ln. You're looking for that. If you're using a TI-84, you're going to press the ln button at the middle left, middle to lower left, and then enter 7, and then press the enter button at the bottom right. And so the answer is going to be approximately 1.946. Again, round to the nearest thousandth place. Okay. So let's try one more of these before you try one on your own. We're doing the same thing over and over again. We are transforming the logarithmic equation to an exponential equation. And this little number here, that's always the base. This number here is always the exponent. And this number here is always what goes on the other side. It's the same thing over and over and over again. So, we can use exponent rule number 6 to change that to e to the 1 power, or e to the first power, and obviously x is equal to 1. We can see that. So did we need a calculator? No, we did not need a calculator for that problem. And what is the answer? Well, x, which is equal to natural log e, is equal to 1. So in that case, we actually used logarithm property 3. That tells us that if these two numbers are the same, then the answer is always going to be 1. Again, that's just a shortcut. We used property 1, but if you want to jump right to the answer, you can use property 3. Okay. So it's time for you to try. I'm going to give you one more chance to take a picture of those logarithm properties. And I'm going to leave these problems in the window, and I want you to try number 13. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. So I want you to take a picture of all these problems, because they'll help you in the next problem, problem number 14. Okay, so I want you to try problem number 14. And remember, you have to figure out if you need a calculator. Do you need a calculator for this problem? Well, convert it to, first make a logarithmic equation by setting it equal to some variable, and then convert it to an exponential equation, and you'll see pretty quickly if you need a calculator. If you can solve the exponential form of the equation without a calculator, then you don't need a calculator, but we'll see what happens here. Try number 14. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 15. When you come back, we'll do it together. Okay, we're back. So if you got that right, good. Try number 16. When you come back, we'll do it together. Okay, we're back. So if you got that right, good. Okay, try number 17. We have another base 10 logarithm. When you come back, we'll do it together. Okay, we're back. So we say log 10, but what we really mean is log base 10 of 10. So go ahead and try number 18. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay. So I just want you to be aware that these problems can get more difficult. A lot of students might be thinking, you know, these problems seem difficult. They seem really strange, and you know, I don't like doing logarithms. Most students don't really like logarithms because they're scary. But I just want you to know that these problems can get a lot more challenging. I'm not giving you really difficult problems. So we're just going to do a couple just to give you an idea that these can get more difficult. So first of all, let's rewrite this as log base e of 1 over e squared. That's what ln means. It means log base e, right? And let's set that equal to x. Let's translate to an exponential equation. So we have e to the x power is equal to 1 over e squared. So this little base here, that went there. The x went there, and all of that, of course, went there. That's just logarithm property 1. That's just a definition. It's nothing that you have to worry about. It's just mathematicians have defined that this this notation is the solution to this equation. That's all that means. So if you have this equation, the solution to the equation is this expression. It's just they're just coming up with a name for the solution. That's all that is. So now we're stuck. We don't know what to do, and we're completely stuck. But we can use exponent rule number 8, which tells us that we can bring that up to e to the negative 2 power. By definition, this expression is equal to that expression. That's one of the exponent rules, number 8. We talked about the exponent rules in the previous class. So now we can see that x is obviously equal to negative 2. Did we need a calculator for that? We did not need a calculator. And the answer, natural log of 1 over e squared is equal to negative 2. So there you go. So that's just one example of how these problems can get a lot more difficult. We're just doing basic forms of these problems. So if you're having trouble with the basic forms, if you're hopelessly confused with how to work with these logarithms, then again, that suggests a big problem. Okay, so I want you to try number 20. You're going to need to use exponent rule number 9. So that's the rule that says that if you have the nth root of some x, then that's equal to x to the 1 over n. I don't know if it's stated in that way, but you can check your files. Try number 20. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. If you had some trouble with that, that's okay. You may need to review the exponent rules. But there we go. So that was some review on logarithms. You're going to be expected to know the basic rules of logarithms, how to transform a logarithmic equation to an exponential equation. So now we're going to review some basic function notation. So it says to use the graphs below to find the following values. And so we have a graph. This is f of x, and we're told to find f of 3. Now what does that mean? Well, it means find the point on the graph that has an x value equal to 3. So isn't it true that this purple point here has an x value of 3? So 1, 2, 3. That point has an x value of 3, right? So here's the question. What is the yellow y value of that point? The y value is -1, right? So that means that the answer is -1. F of 3 is -1. So what this is asking is, if your x value is 3, what is your corresponding y value on the graph? That's all that's really asking you. So if x is -1, what is y? So now we go out to the left and we find the corresponding point. The y value of this point is 1. So function notation is very strange and very confusing for students, and it takes a long time to get used to it. When you take your first calculus course, that's generally when you master function notation. But before that, students typically don't have enough fluency and they have some problems with it. So in number 22, we dealt with this point here. For number 23, we're going to deal with this point because x is 0. The x value of that point is 0, right? What is the y value? Well, the y value is 2. So the answer is 2. So these y values are considered to be the outputs of the function, and the inputs of the function are the x values. So if the x value is 5, 1, 2, 3, 4, 5, what is the corresponding y value? Well, that's just going to be 1. So that point we just dealt with is this purple point right here. So this is just showing you how to deal with function notation. Okay, so number 25, if the x value is -3, what is the corresponding y value? So I'm going to move out -3, 1, 2, 3. I'm going to find the corresponding point. You see that purple point? That point has an x value that's equal to -3. What is the y value of that purple point? Well, it's 1. So that's what they're asking. They're just asking, if your input is -3, what is your output? It's 1. The inputs are the x values, the outputs are the y values. If your output is 0, what is your input? Or excuse me, if your input is 0, what is your output? It's just asking for the y value of this point here where x is 0. So obviously that would just be 0. If your input is -1, what is your output? Well, you move to the left 1, and then you find the corresponding point. The y value of that point is 2. So you can think about it in terms of x values and y values, inputs or outputs, however you want to think about that. So if the x value is -4, what is the corresponding y value? So let's go to the left. 1, 2, 3, 4. What is the y value of that point there? The y value is 0. Okay. So I want you to try some of those problems, see what you can do. I know this is strange, but this is the type of thing that we're going to have to do in calculus, unfortunately. You're going to become an expert when it comes to function notation after your first calculus course, but as of now, students may not know the notation as well as they should, so we have to practice. So try numbers 29 through 32. See what you can do. When you come back, we'll do it together. Okay, we're back. If you got that right, excellent. Go ahead and try numbers 33 through 35, and when you come back, we'll do it together. Okay, we're back. So you got those answers. Good. Okay, so we reviewed complex fractions, logarithms, and function notation. And now we're going to review piecewise functions. We went over these in my intermediate algebra course, but we're going to have some different types of problems here. Piecewise functions are used quite a bit in the calculus curriculum. They're not the most important thing, but they are a part of the calculus curriculum. You're going to have to know how to deal with them. When students see piecewise functions, they usually get pretty depressed because they don't like them. They seem really scary. Some students are so afraid of this that they just give up when they see it. They don't even want to try. But it's really not that difficult. You just need to know how to use these functions. So we want to find these values, and what this is asking us to do is to plug in -6 for one of these functions. But which one do we use? We can't use both of them at the same time, right? We either have to use the green one or the blue one, so which one do we use? Well, it depends on what we're being asked to do. We're asked to find the output when the input is -6, but we only use one of these expressions at a time. So when we use -6, we have to use the top expression. Why? Because it says use this expression when x is between -10 and 4. -6 is between -10 and 4, right? So that means we use this expression, this x plus 8. So our input is -6, and we add 8 to that, and we get 2. So there you go. What about when x is 4.1? Well, in that situation, the value is between 4 and 22, so we actually use this expression here. So it's going to be natural log 4.1. We plug in our x value into this function because our x value is between 4 and 22. But if our x value were between -10 and 4, or equal to 4, then we wouldn't use this expression, we'd use the top expression. We could just keep our answer like that. So what about when x is 4? Well, we use this expression up here because it says when x is less than or equal to 4, you use this expression. So we have 4 plus 8, which is 12. Again, we use the top expression. Okay, so now e squared. E is a constant, and we need to know if e squared is between 4 and 22 or if it's between -10 and 4. So if you're using a TI-84 plus, then you can push the blue second button and then the LN button at the bottom left, and you should get e to the something power. Enter 2 and then press enter, and we get approximately 7.389. So is this number between -10 and 4, or is it between 4 and 22? Obviously 4 and 22, so we use the bottom expression. So ln, we plug in e squared. Well, remember ln is log base e, and remember we have that property number 2 that says that the expression is just equal to 2. Now, if you don't want to use that shortcut property, then you can just set this logarithm equal to y, and then you can use logarithm property 1 to translate it. So I'm going to translate that blue equation. So we have e to the y is equal to e squared. Well, obviously y has to be equal to 2, right? That's what we're looking for, is y. So that's just one of many examples where you're going to be expected to know how to deal with logarithms. And your calculus teacher is not going to show you how to do it. You're just going to be expected to figure it out. So that's why calculus is considered to be so difficult, is you have to understand previous math concepts, and very few students have a mastery of all the concepts. So let's do another one of these. So this problem is a little different from the piecewise functions that we've seen in my intermediate algebra course. because over here we have expressions where there's only one inequality for each expression. In my intermediate algebra course and in this previous problem, we had a situation where you use the top expression when x is between two numbers, and the bottom expression when x is between two other numbers. But in this situation, this just tells us when x is any number bigger than 2, you use the top expression. And when x is any number less than 2, you use the bottom expression. Also, when x is equal to 2, you use the bottom expression. So that's what that means. So we need to know if we're going to use this expression or this expression to find our value here. Well, we're told that the input is -4, so that's when x is less than 2. So we use this expression here. So we have -4 plus 4 cubed, which is 0 cubed, which is 0. Now what if your input is 3? What if your x value is 3? If your x value is 3, then 3 is bigger than 2, so that means you use this expression up here. So we have 5 to the 3 plus 1 minus 1. So that's 5 to the 4th power minus 1, which is 625 minus 1, which is 624. Okay, so now we're going to plug in 2 for the x value. It says here when x is less than or equal to 2, you use this expression. So we're going to use that expression. Again, the identity of the input tells you whether or not you're going to use the bottom expression or the top expression. So we get 216. Now the input is -2, but -2 is less than 2. So we're going to use the bottom expression. So we have -2 plus 4 cubed, which is 2 cubed, which is 8. So there you go. Okay. Whoops, I forgot to write the answer on that one, I guess. Sorry about that. I may have just pressed the undo button accidentally. So you can get a picture of these problems if you want. We'll do one more problem before you try one on your own. So we need to know if we're going to use the blue expression or the yellow expression. So our input is -7. It says here when our input is greater than -8, then you use the bottom equation. So -7 is actually greater than -8. So we're going to use the bottom expression. So we have the absolute value of -7. So that's a double negative. You have to be careful of that. Now we get the absolute value of 7 plus 4. Remember, if you're finding the absolute value of a positive number, it doesn't really change the positive number, it just stays positive. So if the input of the function is -7, then the output is 11. Okay, so if we're going to plug in 100, 100 is definitely greater than -8. So we have the, we're going to use the bottom equation. Absolute value of a negative number is whatever the positive version of that number is. So if it's a positive number, you don't change the number. If you have a negative number in an absolute value, you change the negative to a positive. That's just how absolute values work. This is something we learned in my math curriculum. So if you're coming from a different curriculum and you have never seen absolute values before, again, that's an indication that there's something wrong. Okay, so now the input is equal to -8. It tells us in that situation, when the input is equal to -8, the value of our output is just 5. So that's all we have to do, really. It's just 5. So now our x value, our input is negative 8, which is less than, or excuse me, it's negative 9, which is less than negative 8. So we use the top expression, but again, whenever our x value is less than or equal to negative 8, we just write this constant number. Okay, so now it's time for you to try. So I want you to get a picture of these piecewise functions at the right, and you can use number 38 to help you with number 39. So go ahead and try number 39. When you come back, we'll do it together. Okay, we're back. So 100 is definitely greater than 0. Okay, so if you got that one right, excellent. So I want you to try number 40. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Now if you wrote a decimal, that's okay. But the decimal should be equal to negative 17.849, and you can round it off to whatever you want to. Okay, so I want you to try number 41. When you come back, we'll do it together. Okay, we're back, so if you got that one right, excellent. All right, we have one more piecewise function to practice. Try number 42. When you come back, we'll do it together. Okay, we're back. This is an example of the type of thing that you're going to be expected to know. Now we're going to graph functions using the library of functions and transformations. I want you to get a picture of the library of functions at the left. You're going to need those as we move along today in the class. This is a very powerful tool for students when they go into upper mathematics. So graphing is a huge part of the math curriculum, and it's very important to be able to visualize functions on graphs. And so you're going to be expected to graph some equation that you're given, but it's much more convenient if you can just graph that equation quickly, and that's what the library of functions and the transformation method allows you to do. But there's a problem with this method, and that is when you get to some more complicated equations like this, students often do not perform those transformations in the right order, or they really don't, they misunderstand how to use transformations and how the parent graph is going to change based on the form of the equation that they're trying to graph. And so when you get into more complicated equations like this, the method kind of breaks down unless you really have a good understanding of how to do this. Now, if you're just performing one transformation, as what we're going to do in this problem, then usually it's not a big issue. But well, let's get into it, and I'll show you what I mean. So we're going to start with our parent equation. So you see that this is the quadratic function. So that's our parent equation. And then we're going to modify that equation. We're going to replace x with x minus 3. So there's only one transformation necessary. So the way that this works is we start with our parent equation and our parent graph. So let me draw the parent graph. It looks something like that. So we start with that parent graph, and all we're doing when we move to the orange equation is we're replacing x with x minus 3. So all we're going to do is move 3 units to the right. Now, if you took my intermediate algebra course, you know that when you subtract from x, you move to the right. When you add to x, you move to the left. So it's the exact opposite of what you would think. The same is true for y. If you replace y with y plus something, then you actually go down, not up. If you replace y with y minus something, then you actually go up, not down. So whenever you're graphing with transformations, the direction that you move or whatever you're performing is actually, it ends up being the opposite of what you would think. But that's it. As you can see, we used a transformation. This is a translation when you move to right, left, up, or down, and it was easy. It wasn't really that big of a deal. There was no real confusion about, how to graph that. But now we have a case where we're going to have to use 2 transformations on the parent graph. So what is our parent equation? Well, it's the reciprocal equation, and the parent graph. The parent graph has 2 asymptotes, one on the y-axis and one on the x-axis. And if you recall, there's 6 reference points that we typically use. 1, 1, 1 half, 2, 2, 1 half, -1, -1, -2, -1 half, -1 half, and -2. Now, if you forget those 6 reference points, you can just use the equation. Plug in 1 for x, you get 1 for y. Plug in 2 for x, you get 1 half for y, so on and so forth. So let's connect the dots, and that is the parent graph. Okay, but now we're going to start to modify things. And when we replace x with negative x, that means we just reflect the graph of this equation across the y-axis. That's how it works. If you replace x with negative x, you reflect the graph of the previous equation across the y-axis. If you replace y with negative y, you reflect the graph of the previous equation across the x-axis. That's how reflections work. So we can deal with that really easily. But here, we learned in the previous problem that when you add something to x or subtract something, you move horizontally, left or right. If you're adding to x, then you move to the left 2 units. But the problem is we're not adding to x. You see, adding to x means when you write your new equation, you replace x with x plus 2. We're not doing that. We're adding x to -1 over x. So this is why things can get really confusing. And so in order to really understand what's going on here, we're going to change f of x to y. You see that things are immediately becoming more complicated. And so you might wonder, well, okay, well, what do we do about this? Well, we're not going to give complete instruction in this class on how to do this because this is a huge topic. But you can receive complete instruction on this, very thorough instruction on this in my intermediate algebra course. I have many classes entitled, I believe they're entitled the Library of Relations, Transformations in the Library of Relations or something like that. And also I have classes labeled the Library of Functions. And so I have many classes on that, and you can get complete instruction on that. But we're just going to go over this and give you an idea of the things you're required to know, or you should know. Now, I just want to make it clear before I continue with this that most students don't have a complete understanding of how this works. And even most teachers don't have a complete understanding. So if you don't have this completely mastered, that doesn't mean that you're not necessarily ready for the course. It just means that you do need, even if you don't have complete mastery, you do need to understand the basic concepts of transformations, because you're just going to be required to do this in the calculus curriculum. Um, uh, Either that, or you'll have to make a table of values, and it doesn't work. It just takes too long. So if you want complete instruction, you can go to my intermediate algebra course. So we changed f of x to y just to make the algebra easier, and then we took the 2 and put it on the other side. It's very important to understand that the graph of this equation is the same graph that you get when you graph the purple equation. It's just that the equations are in different forms. But the reason that we changed to this form down here is because now we can see that we're just replacing, I'm going to write y equals, we're just replacing y with y minus 2. So now we're not going to make a mistake when it comes to graphing. Or we know we're doing this in a very systematic way. So we know how to interpret the difference between this graph and this graph very easily. But when the 2 was over here, we didn't know how to interpret the change. We weren't sure how to use the method of transformations. Now, a big issue is which transformation do you do first? Do you do the reflection first, or do you do the transformation first? Well, notice that these modifications are on now opposite sides of the equation. When they're on opposite sides of the equation, it doesn't really matter which one you do first. So we got kind of lucky on that. So I think I'll do the reflection first. So I'm going to replace x with negative x. So what that does is it reflects the graph across the y-axis. So I'm going to take all these points and reflect them, and we get the following graph. So we change the green graph to the purple graph by reflecting across the y-axis. And so now we have our purple graph, but now we're going to change to the orange graph, and we're going to replace y with y minus 2. The only thing that we're doing is just changing y to y minus 2, so we know how to interpret that. That means we're going to move the graph up 2 units. That's a translation. Alright, so I'm going to erase that a little bit. And we need to continue our graph down here. So there you go. So this is the graph of the orange equation. Obviously you don't have to use colors, but that is the final graph. Okay, but because we're doing more than one transformation, things start to get more complicated. And in the next problem, things are going to get even more complicated. But the good news is that you're probably not going to be really expected to graph an equation that is this complicated in most cases. So I don't want to, scare you too much here and make you think that, you're gonna need to necessarily graph that without a calculator, because a lot of times teachers will just allow you to use a calculator. But even then, it's a very convenient thing for you to know how to graph this if you did have to graph it without a calculator. Now notice that we subtracted from y and we moved up, so it's the exact opposite of what you would think. Notice that we replaced x with negative x and we reflected across the y-axis, the exact opposite of what you would think, so just be aware of that. Okay, so now again, the purpose of this is not to scare you, it's just to show you how transformations work and how if you use them improperly, you can get the wrong answer. But as we do this, just be aware that this is a very, very advanced problem, and so most calculus students would have trouble with this. So if you have a little trouble, that's okay. And again, if you want to master this, you can go to my intermediate algebra course. So let's write the parent function there. The parent function looks like this if we graph it. Something like that. And so now we've just got a big mess here. What do we do first? Well, we don't know how to interpret this. We don't know what to do to the parent graph when we just subtract 1 from all this orange mess there. We don't know what that even means. And for that matter, we don't know what this negative 1/2 being multiplied by the absolute value of x plus 1, we don't know what that means. We didn't learn how to really interpret that. So we have to change the form of this equation. Now again, what I'm talking about here may not be familiar to a lot of students who didn't receive really thorough instruction on this. So if you're not sure exactly what I'm talking about, again, you can go to my intermediate algebra course. So I'm going to put the 1 on the other side, and now we can interpret what's going on, you see. Because now we're just modifying the equation of the parent equation by replacing y with y plus 1. So sometimes you have to modify things in order to see what's going on. I'm also going to multiply both sides by -2. And it may not be exactly obvious, but we now have a chance to actually use transformations to graph this equation, whereas up here we just didn't know what to do. The reason we changed to this form is now we have a systematic way of actually graphing, and it's a foolproof way of graphing this equation without making a mistake. But here's probably the most difficult thing. One of the most difficult things in the math curriculum is understanding what order we're supposed to use our transformations. Are we supposed to translate first and then reflect and then dilate, or do we dilate first and then reflect and then translate, or do we which one do we use? Again, that's something that most students don't really have a full understanding of, and even math teachers often don't have a full understanding of that. And we don't have time to go into all of it right now, so we're not going to spend a lot of time on this, but I'm just going to show you some of the things that would be very useful for you to know, even though you're probably not going to be required to graph that equation. It's a very complex equation. So in this particular situation, you need to dilate first. And actually, dilation and reflection can be done at the same time because of the commutative rule of multiplication. So if I replace y with -y, and then I replace y with 2y, in both of those situations, we know what to do. But if I start by dilating, if I have 2y and then I replace y with -y, well, I just end up with -2y again. So that's what I mean by the commutative rule of multiplication. It doesn't really matter if you can just dilate and reflect at the same time. There's not really an issue there. So I'm going to go ahead and do that. So I'm going to divide all the y values by 2. Divide all the y values of this graph by 2. Now again, you might say, well, wait a second, you're multiplying y by 2. But again, with transformations, it's the exact opposite of what you would think. So I'm dividing all the y values by 2, and I get this graph. Okay, but then I'm also going to reflect, because I'm putting a negative on the y. Again, you can think of it as first changing to 2y and then changing to 2 times negative y. So I'm just replacing y with negative y. That's how this works. If you replace negative y or y with negative y, then you just reflect across the x-axis. So our graph ends up looking like this. So we flipped across the x-axis. But again, when you multiply 2 times negative y, you just end up with negative 2y. So there you go. So we did the dilation and we did the reflection. And maybe I should just do that step by step. So we have 2y is equal to absolute value of x, and then we have negative 2y is equal to the absolute value of x. So now we're going to change y, or we're going to replace y with y plus 1. And we can also replace x with x plus 1. These two transformations are happening on opposite sides of the equation, which means you don't have to worry about the order in which you do them. You can just do both translations at the same time. So when you replace y with y plus 1, you move you move the graph of the previous equation down 1. When you replace x with x plus 1, you move the graph of the previous equation to the left 1. So that would take us to here. And our graph should look something like that. So let's double check, make sure everything is right. Everything looks good. So now we can erase these graphs, and that is how you graph using transformations. Now, I don't want to scare you into thinking that you're going to be asked to graph something this complicated. Normally when you're doing transformations, you're doing simple transformations like this, or maybe one that requires 2 transformations. It's very possible that you could be asked to graph something like this, but usually you'll be allowed to use a calculator. And you should also be aware that you can still use this equation to find various points. You don't have to graph the entire thing using transformations. You can combine, the table method with the transformation method to do this. But again, you're not going to necessarily be asked to graph something this complicated, but you can see that this is a very powerful tool. What if you did have to graph something this complicated without a graphing calculator? What would you do? Well, transformations is going to help you to do that quickly. Now, you might say, well, that wasn't very quick. I mean, that took a long time. Well, if you know how to do this, if you know what you're doing, you can graph this in probably under 10 seconds if you know how to use the transformation method properly with the library of functions. But that's it. That's the transformation method. Again, it's one of the most challenging, or one of the most intimidating things in the math curriculum. Like I said, a lot of math teachers don't even have a complete understanding of this. Now, I want to point something out here. We dilated and reflected first, and then we translated. What if we translated first and then dilated and reflected? Well, if we did that, then we would go from here to here, we'd replace x with x plus 1, and we'd replace y with y plus 1. And then when we reflect and dilate, we would then multiply y plus 1 by negative 2. And we don't really know how to interpret that. We know that if you replace y with 2y, we're dividing all the y values by 2, but we didn't replace y with 2y. If you replace y with 2y, all you do to modify this equation is put a 2 in front of the y. That's replacing y with 2y. Then you take the graph of this equation and divide all the y values by 2. But we didn't do that. We multiplied y plus 1 by 2. Actually, negative 2. We did the reflection and the dilation at the same time. So we don't know how to do that. And by the way, the reason we did that is because that's the expression we're looking for. That's the way that we wrote it. Now, if we wrote that expression differently, if I distributed the negative 2, then we could actually translate first. So it just depends on how the expression is written. But we wrote it this way, so that's what I want. But again, if I write it that way, I can't translate first and then dilate, because we just don't know how to interpret that. So again, these are all things that we went over in my intermediate algebra course in detail. So let's move on to another problem. And like I said, most problems are not going to be this difficult to graph. But if you do need to graph something this complex, you have a powerful tool to do that if you know how to do these transformations properly. So let's go to another problem, but now let's go back to a problem where we're just doing one transformation. Again, I don't want to scare you by thinking that making you think that all these problems are going to be this complex, where you have 3 transformations. So first of all, we need to write the parent equation. And again, if you don't have a picture of the library of functions, make sure to get that. So now we're starting with this one here. Now, when we replace x with negative x, okay, so if I replace this equation with this, we know what to do. We know how to modify the graph of this equation to make it look like the graph of this equation. The problem is we're not replacing x with negative x. We're replacing root x with negative root x. We don't know how to deal with that. So this is another situation where you have to modify the equation. We're going to multiply both sides by negative 1, and now our negative is on the other side. So now we're just replacing y with negative y. Well, now we can understand. This is just a reflection. And because the negative is on the y, we're reflecting across the x-axis. So we're taking our parent graph and reflecting across the x-axis. So our new graph looks like that. So that was pretty easy. Again, not all of the transformations that you're going to have to do are going to be that difficult, or not all the functions that you're going to graph are going to be that difficult to graph, as long as you have your library of functions memorized. Now, if you don't have your library of functions memorized, then you're going to have to graph the hard way every time, or use a calculator. But again, that's not practical, because with the advanced placement exam, you're going to be expected to know how to interpret equations and how to graph them without doing it on your calculator every time, or with a table. So now we are going to do 2 transformations. Let's write the parent equation and draw the parent graph. So that is the parent graph. And again, the question is, how does the parent graph change based on these blue modifications? Well, we know what to do when we just replace x with x plus 1. We just move the graph to the left 1 unit. But we don't know what to do when you multiply x plus 1 cubed by 2. We don't know what that means. We don't know how to interpret that. We didn't learn how to do that in my intermediate algebra course. So what we're going to do is replace f of x with y just to make the algebra easier. And then we're going to divide both sides of the equation by 2. And again, it's so important to understand that the graph of this equation is the same graph that you get when you graph this equation. The difference is now we can see how to modify this graph here. Now notice that the modifications are on opposite sides of the equation. So what that means is it doesn't really matter what order we use. So do you want to translate first, or do you want to dilate first? Doesn't make any difference. I'm going to, I think, translate first. So we replaced x with x plus 1. So what does that do? That just moves the graph to the left 1 unit. But then we're going to divide, or excuse me, we're going to multiply all the y values by 2. And that's going to give us y over 2 is equal to x plus 1 cubed. So again, it's the opposite of what you would think. You would think we would divide all the y values by 2, but that's not correct. We're going to multiply all the y values by 2, and we get the following graph. Something like this. Again, your graph doesn't have to be perfect. My graph doesn't really look right. Let me try to draw that better. Looks something like that. So anyway, that is the graph. So we have to change the form of the equation to understand what's going on, and we have to be careful that we don't graph our transformations in the wrong order. Okay, so now here we have another really extreme example of graphing using transformations. Most calculus students don't know how to do this without making some sort of error. They don't know how to do it with transformations. You can enter it into your calculator. They know how to do that. They can try to come up with a table of values, which in this case really wouldn't work. I mean, that would just take forever, and you'd get a lot of weird numbers. And so it's not really practical to use those methods. Well, if you don't have a graphing calculator, obviously you can't do it that way. So it's very useful to be able to do this without a calculator, but most students don't know how to graph a complicated equation like this. Even most calculus students don't know how to do that. So a lot of times, well, in most cases, teachers really aren't going to make you do this, but I just want you to be aware of how to do this if you really wanted to, but this is kind of an extreme example. So let's draw the parent equation, or write the parent equation and draw the parent graph. Now you see we have a logarithm. This is where your logarithms are going to come in handy. If you know how to choose your values, it's going to make this a lot easier to graph. So first of all, we have a vertical asymptote on the y-axis. When this number is 1, the value of the logarithm is always 0. If this number is the same as this number, the value of the logarithm is always 1. So if you plug in 2 for x, you get 1. And if you plug in 4 for x, well, the only way we can really understand what that is by translating to an exponential equation. In fact, you can do that for every one of these. If you want to know what happens when you plug in 1 or when you plug in 2, just transform into an exponential equation and you can find the answer. So that's why we did all that. So what is y? Well, y is 2. When x is 4, y is 2. So now we connect the dots, and there you go. So that's why we need to know a little bit about logarithms. We can't be ignorant about logarithms. We need to know how to deal with them in the math curriculum. So now the question becomes, what do we do first? Because notice that all this math is on the same side of the equation. That means if we don't do this math in the right order, in other words, if we don't do the transformations in the right order, then we're going to get the wrong answer. And that's what makes this so challenging. So what do we do here? Well, it just depends on how the expression is written. If you factor out negative 3, so you get this expression, the way that you would graph this using transformations would be, or the order that you use when you graph your transformations would be different than the order you use here. It just depends on how the expression is written, but I'm going to keep it the way it's written. In this case, you have to translate first. The way that it's written, you have to translate first. If you don't translate first, you're not going to get the right answer using the methods that we learned in my intermediate algebra course. So we're replacing x with x plus 6. What do? We just take the entire graph and move it 1, 2, 1, 2, 3, 4, 5, 6 spaces over. Okay, and then we're going to, I'm going to dilate and reflect at the same time, because it doesn't really matter. Based on the commutative rule of multiplication, it doesn't matter which one you do first. So replacing x with negative x, that's going to reflect across the y-axis. So we're going to have, and in fact I can't really do that. We're going to be we're going to be over here. So rather than do that, I'm going to dilate first. So I'm going to divide all the x values by 3. So that's going to give us it's going to change to that number, and this is the x value of this point is 5, so it's going to change to 1 2/3, and that's about all we can do. We could find some other points, but I'm not going to make you do that right now. Now see the pink asymptote? That's at x equals negative 6. If you divide by 3, it takes you all the way to negative 2. So we dilated, but we still have to reflect. Again, it doesn't matter what order you do this in because of the commutative rule of multiplication. So we're going to reflect across the y-axis. That puts our asymptote over here. And this point is reflected. And this point is reflected. And so there you go. Now again, this part of the graph over here is probably not that accurate because I'm not choosing points over there. It's kind of hard to find points that are easy to work with. But the graph doesn't have to be perfect. We're just getting the main idea of the graph. So that is your graph. Now, again, if you reflect first, let's say that you change to log base 2 of negative 3x, you reflect and dilate first, then you add 6. Well, it's not going to be right, because you're not adding 6 to x. You're not just replacing x with x plus 6. You're adding 6 to negative 3x. See, that's not the same thing as adding 6 to x. So again, this can be pretty challenging stuff. So I want you to get a picture of the library of functions and problems 43 through 45. And I'm going to leave problems 46 through 48 in the window, and I want you to try number 49. Now we're starting out easy. We're starting out with just one transformation. But I want you to be aware that you're going to need to put that 2 on the other side. We don't understand how to transform the parent graph if we're multiplying at the absolute value of x by 2. We just don't know what to do there. We don't know what that even means. So you're going to have to divide both sides by 2. Now we can see what's happening because you're just replacing y with y over 2. And of course the parent equation is that. So go ahead and try problem number 49. When you come back, we'll do it together. Okay, we're back. If you got that right, excellent. Okay, so I want you to try number 50. For number 50, we're doing 2 transformations, and I just want to warn you that you need to put the negative 1/3 on the other side. You need to multiply both sides by -3, and now we can graph it. Now we have a chance. You may have a little trouble with that, but in this form we have a chance. In this form we don't know what is going on. So again, we're trying to use our systematic way of transforming the parent graph so that we can graph these functions. Try number 50. When you come back, we'll do it together. Okay, we're back. Okay, so the graph looks something like that. So if you got that right, excellent. Now you don't have to use different colors. I mean, if you're thinking that you have to use different colors, no, you don't have to do that. Okay, so now we're going into a really, really difficult problem. And notice that all of the math is happening on the same side of the equation, so that means if you don't do this in the right order, then you're going to get it wrong. So if you graph this and you get the wrong answer, you know, that's okay. But I just want you to see that the method of transformations is a really powerful method if you know how to do it. So let's see if you know how to do it. Again, you can go to my intermediate algebra course and review this if you need to. So try number 51, and when you come back, we'll do it together. Okay, we're back. So we don't have time to consider all the points, but that's basically what it's going to look like. So again, you can probably tell that was not exactly easy. That's why this is considered some of the most advanced math, using transformations to graph an expression or an equation like that. So if you had trouble with that, that's okay. It's not the end of the world. I mean, most students will have trouble with that. Most students will probably just give up with that, you know. But you can see that even when it comes to an extremely challenging problem like this, transformations, if we use the method correctly, it allows us to graph that without having to use a table or a calculator. So I want you to get a picture of these problems here to help you. And the good news is we're back to 1 transformation. We're going to do 3 more problems, but the first problems are going to start. The first problem just starts with 1 transformation. Now again, we don't know what to do when you're adding 3 to x cubed. We don't know what that means. So we need to put the 3 on the other side, and now we know what's going on. Now we're just moving the graph. We're translating it. So go ahead and try number 52. And when you come back, we'll do it together. Okay, we're back. When you only have 1 transformation, it's really not that big of a deal. So go ahead and try number 53. Now we have 2 transformations, so things are going to get complicated. And because all the math is happening on the same side of the equation, you have to make sure you do the transformations properly in the right order. If you reflect first and then translate, you're going to get the wrong answer. So try number 53. When you come back, we'll do it together. Okay, we're back. So there you go. So if you're careful, you can graph a function that requires 2 transformations. But when you get to 3 transformations, that's when a lot of students just lose it. They lose control. So number 54 is going to be a challenge problem. Now again, if you want complete instruction on this, you can go to my intermediate algebra course. But try your best, and when you come back, we'll do it together. Okay, we're back. So there you go. That is the graph of the orange equation. So again, if you don't have a complete mastery of this, then you can join the club of 99% of all calculus students. It's not something to be overly concerned about, but you can see that if you really know this method, it's a powerful way to avoid having to do a lot of unnecessary work. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1, number 2, number 3, number 4, and number 5, number 6, number 7, and number 8. But don't go before you get your homework assignment. Remember, the homework is not optional. You must do it completely and correctly and neatly and keep it in order in your binder. So here's screenshot number 1 of the homework, and screenshot number 2 of the homework, and screenshot number 3, and here's the answers to the homework. It's not enough just to attempt the homework, it must be done correctly. So if you get the wrong answer, you'll know that because you'll check the answer, and if you get the wrong answer, go back and do it correctly. Again, the homework must be done correctly. So get that homework done, and I'll look forward to seeing you in the next class.